Hi, my name is Ben Eisenbach. I'm going to be presenting our work entitled Rewriting History with Inverse RL, Hindsight Inference for Policy Improvement. This is joint work with Young, Sergey, and Russ. I'm really excited for the day when a robot moves into my house. There are so many things I'm going to have this robot do. Rearrange things, automate things, and most importantly, clean up my desk. Now, the only problem is that if the robot has to learn all of these things through trial and error, it'll take an extraordinarily long amount of time. How can we efficiently teach a robot to solve multiple tasks? This is the problem we consider in this paper. Formally, this is the problem of multitask reinforcement learning. We assume that we take as input some data set of experience. Experience here corresponds to state action pairs, as well as a collection of reward functions, each corresponding to a different task. For example, we might have one reward function corresponding to picking up a block, and another reward function corresponding to putting a block in our drawer. Our aim is to acquire a policy for solving each of these tasks. The main challenge of multitask reinforcement learning is, given some collection of experience, as well as a set of tasks, which experience should we use for solving which tasks? Now, intuitively, we should use experience for solving tasks for which this experience would be useful. One way of encoding this intuition is as follows. Would a human watching the robot performing one task mistakenly think that the robot was solving a different task? If so, this is a good cue that this experience would also be useful for solving this other task. Now, this problem of inferring what do we think the robot is trying to do is a well-studied problem known as inverse reinforcement learning. The main idea of this work is that we can use inverse reinforcement learning to automatically share experience across tasks. To look a little bit more at inverse reinforcement learning, watch this video on the right and try to guess, what is the robot trying to do? You probably can guess that the robot is pushing the door out of the way so it can push the blue button. Inverse RL is the problem of automatically answering these sorts of questions. One way of viewing inverse RL is as solving the opposite problem as regular reinforcement learning. Whereas reinforcement learning takes a reward function and tries to produce the optimal policy for that reward function, inverse RL does the opposite. It observes an agent performing a task and tries to infer, what is this agent trying to do? As we'll see in our method, which we introduce next, we can use inverse RL to actually help solve a reinforcement learning problem to help maximize reward. Let's now introduce our method, which is a general method for multitask reinforcement learning. We call our method Hindsight Inference for Policy Improvement, or HIPI for short. And to show how it works, let's consider a manipulation task with 3 tasks, including, say, lifting up a block. We first gather some experience, and then we run inverse reinforcement learning on this experience. For example, in this top experience, we might infer that the agent is trying to lift up a block. Therefore, in the third stage, we'll use this experience for learning the task of picking up a block. Now, we might also think that this robot might be trying to lift up the block so it can put it in the drawer. Therefore, we might also use this experience for learning the task of putting a block in a drawer. One thing that's important to note is that if we didn't share experience across tasks, much experience would end up wasted. It's also important that we don't need to solve tasks entirely. As long as we make some progress on some tasks, HIPI will be able to learn. In our paper, we explored 2 methods for learning from relabeled experience, using off-policy reinforcement learning or using behavior cloning. Let's see how those work. The first approach, which we call HIPI-RL, learns from the relabeled experience using off-policy reinforcement learning. We first sample some experience from our replay buffer, and then run inverse RL on this experience. Finally, we apply an off-the-shelf, off-policy reinforcement learning algorithm to this relabeled experience. The second option, which we call HIPI-BC, learns from the relabeled experience using behavior cloning. As before, we first sample some experience from the replay buffer, and then run inverse RL on this experience. In the third stage, we learn from this relabeled experience using behavior cloning. Now, one of the neat things about HIPI is that we can show that a number of prior methods are actually special cases. In particular, a number of prior works have looked at goal-conditioned reinforcement learning. And goal-conditioned reinforcement learning is a special type of multitask RL where tasks correspond to reaching a certain goal, such as the goal state where a block is in a drawer. Now, a number of these prior goal condition methods use an idea called goal relabeling, which works as follows. Let's say that we tell the robot, go towards the goal where the block is in the goal. And the robot attempts that task, but in doing so, it fails, and it accidentally drops the block in the trash can. But we say, no worry, we'll use this experience for learning to reach the goal that was actually reached at the end of the episode. Now, one of the neat things we show in the paper is that this idea of relabeling experience with the goal that was actually reached is actually a special case of inverse reinforcement learning. Now, this observation is exciting because it helps understand and unify a number of prior methods. Goal relabeling has been applied to a number of off-policy RL algorithms, most notably hindsight experience replay. And in light of this observation, we can view these prior methods as a special case of Hippie-RL. Goal relabeling has also been applied to a number of prior methods that do goal-conditioned behavior cloning. And we can also view these methods as a special case of Hippie-BC. In summary, goal relabeling methods are a special case of inverse RL, and Hippie can be viewed as a generalization of these methods. Now, goal relabeling is often presented as a heuristic, albeit one that works especially well on many settings. One of the neat things we show about Hippie, which uses inverse RL to relabel experience, is that it actually maximizes a well-defined reinforcement learning objective. In particular, we show that this objective after relabeling is larger than the objective before relabeling, and the amount that this objective improves is governed by how much the task labels change when we do relabeling. Let's look at an example. In this example, we have purple tasks and yellow tasks. So if we collect experience with a random policy, an agent that's told to solve the yellow task often solves the purple task, and vice versa. Thus, when we relabel experience using inverse RL, many of the task labels change. Therefore, we'll expect a large benefit from relabeling when we collect random experience. In contrast, if we collect experience from an optimal policy, an expert policy, then no experience will end up being relabeled, and therefore we don't expect any benefit from relabeling. And this sort of accords with our intuition. If we have the optimal policy, relabeling won't help. Let's move on to some experiments. On this task, we control a robotic arm, and we want to move the robot's hand to reach a certain red region. The red region turns green when we reach it. Different tasks here correspond to reaching different goals. We observe that our method, Hippie, effectively solves this task. But compared to a number of alternative approaches that share experience across tasks in different ways. For example, random experience shares experience collected from one trajectory for a random task. Final state relabeling, or hindsight experience replay, uses experience to learn to reach the goal that was actually reached at the end of the episode. And we observe that these alternative approaches struggle to solve these tasks. We explored a range of tasks. And to look at performance, we'll plot the cumulative reward across training. We'll show our method in blue. And the most similar method is hindsight experience replay, which struggles to solve many of these tasks. Now, to give some intuition for this, hindsight experience replay only learns to reach the goal that was actually reached at the end of the episode. In contrast, our method, Hippie, looks at a trajectory and says, what goals might you have been trying to reach? Not only the goal that you actually reached, but what other goals? And thus is able to use a single trajectory for learning many tasks. Now, we also compared to sharing experience randomly, and on many tasks, this was actually a surprisingly competitive baseline. Other relabeling strategies, such as looking at future states in a trajectory or sharing no experience at all, struggle to solve many tasks. The main takeaway from this slide is that inverse RL, as done by Hippie, is an effective mechanism for sharing experience across tasks. Now, one of the most exciting things about Hippie, of using inverse RL to share experience, is that it's applicable to tasks beyond just goal reaching. We explored a couple settings like this in our paper. On this walker task, the reward function is composed of a number of different terms added together with different weights. And these terms correspond to how fast the agent is running and whether it's remaining upright. And typically, tuning these different coefficients is rather manually intensive. And one of the cool things is that Hippie tells us how to automatically set these parameters. Given some experience, we run inverse RL to say, you should set the parameter for the first term to 5 and the parameter for the second term to, say, 3. As a second example, we looked at a robot manipulation task. This looks like a goal-reaching task where the robot has to reach a certain goal, but it also has to get within a certain margin of that goal. Now, typically, this margin parameter requires some manual tuning. When we apply Hippie to this sort of task, we can treat this margin parameter as part of the task definition. Then, when given a trajectory, we can say, Hippie, we can use this trajectory to learn how to reach, say, this goal within, say, this margin. In summary, the main idea of this work is that inverse RL provides an effective mechanism for sharing experience across tasks. And the intuition is that if a human mistakenly thinks that a robot solving one task is actually solving a different task, and this is a good cue that we can use this experience for solving this other task. Now, there are many things I didn't get a chance to talk about, such as how the partition function from inverse RL automatically normalizes the difficulty of different tasks for Hippie. Please check out our paper for more information. We've also released our code so you can build on it. Thanks.